All right. Good morning, good afternoon, everyone, and welcome to today's webinar on multi-objective LFP cathode design, combining DOE methodology with machine learning to accelerate battery development. My name is Simon, and I am from the product marketing team here at Monolith, and I will be your host for today's session. Before we begin, I'd like to share a few housekeeping items. This webinar is being recorded, and both the recording and the slides will be made available to all participants afterwards. We'll send these material via email to everyone who registered, so you can look through the content in your own time and maybe replay some bits that you're interested in looking over again. If you have some questions throughout the presentation, there is a Q&A function that you can use, and we will be able to see the questions as the panelists, and it will monitor questions throughout the webinar. If appropriate, I will interrupt the speakers with a small question here or there, and if the question is relatively simple and small, I will answer it in the chat. Otherwise, we have reserved 10-15 minutes at the end for a Q&A where we will talk and discuss any questions that you might have. Now, I'd like to quickly take a chance to introduce Monolith. And we are a company that for the past 6-7 years have been in the business of helping engineers harness the power of machine learning. We've done over 200 to 300 projects in machine learning and applying AI for engineering test labs. And we really focus on empowering engineers to use AI to solve even their most intractable physics problems to get new products to market faster. So it's really all about these projects and difficult engineering physics that we need to deal with in the test lab, all these different behaviors that are difficult to model. We look at these problems and try to solve the intractable nature of these problems. So what really sets us apart is that we have developed, through our history of collaboration with our clients, a machine learning platform that is powered by the cloud and designed for the engineer, but scalable for the enterprise so that it can be used across large teams and share data across an entire organization. We have a team of data scientists that works constantly with the engineering project team to see what are the best algorithms, how can we fine-tune them and develop them in the best way so that our platform has these best unique AI algorithms that are specifically designed for engineering test labs in mind. And you'll get a preview of that later on when Casper goes through the demo, and James is going to cover a few more of our use cases in detail. And finally, and maybe most importantly, we have a team of dedicated customer success team that are specialists, all ex-industry engineers who have worked on these projects before and now have learned how to best apply machine learning and AI to solve these problems in the test lab. They know exactly which algorithms work best and which tools will help the engineer achieve their test goals more efficiently and as fast as possible. So let me quickly introduce today's speakers. We're very fortunate to have a few people join us today. So we have James from our account executive team. So James, would you like to quickly introduce yourself?
Thank you very much, Simon. And yeah, great to see so many people on the webinar this afternoon. My name is James Mitchell. I'm a mechanical engineer by background. I've spent the last 10 years in industrial and automotive testing with a particular focus on designing and deploying data systems in test environments.
Thank you, James. And with us, we also have Casper Vaniak from our solutions team. So Casper, would you like to quickly introduce yourself as well?
Yes, thank you, Simon. Hi, everyone. My name is Casper Vaniak. I am a customer success and solutions engineer here at Monolith. I have a background in aerospace engineering and previously worked in new product development at Dyson. At Monolith, I've led and supported a wide range of projects across the automotive, aerospace, and battery industries, helping engineers accelerate innovation with AI-driven solutions.
Perfect. Thank you very much, Casper. Before we go in, I'd like to quickly walk through the agenda of what we will be discussing today. So we're going to start with a quick overview of the fundamental challenges in battery development, and then we will explore specific electrode design optimization issues, what are the key challenges, and James is going to be showing us a bit more background there. Then Casper is going to show us a demo of how we perform multi-objective optimization in Monolith with a LFP example. So Casper is going to introduce all about the data set and how we perform the analysis. And then we will talk about how we can really integrate this workflow of using machine learning for an iterative approach and how that compares to the traditional DOE style, how you can scale that up for an enterprise, an organization, and across different projects. So without delaying any more, I will now hand over to James. Over to you.
Fantastic. So thank you very much, Simon. Thanks for the intro. We're speaking to a lot of OEMs in the market at the moment, and what we're really hearing from the industry players is that it's a really challenging market out there for them at the moment. Everyone is being pushed really hard to compete with the Chinese manufacturers and the Asian manufacturers, who've certainly got a bit of a walk on Europe and the US at the moment. Just to pull out one example, we recently spoke to a large German OEM who told us that their two main priority areas were to reduce their R&D cost and to increase their usage of AI in the product development space. And I suspect they might have missed one slight point within this, which is also, and what we hear a lot, is another major objective is to reduce the time to market for these products. So those three challenges are driving the industry response, the market challenge, and are a route to driving competitiveness within the product development space. Now, if we take a look at those three objectives, they're all very much interlinked. And what we can show today is that increasing the use of AI is able to reduce the R&D costs and reduce the time to market. So, for example, on one project, we've been able to take 50% off a customer's time for each loop of iteration of battery chemistry, and we've estimated that saved them around about $500,000 on each test campaign. But probably the bigger opportunity is in the time to market piece. The Volta Foundation report last year estimated that the cost of a missed SOP is around 1.1 million euros a day, and typical delays greater than 3 months. So there is a huge amount of money and saving available to manufacturers by de-risking the SOP, by improving their time, reducing the development time, improving the time to market, and moving forwards. So we're going to look today at a very specific example of how AI and machine learning can help in addressing the two cost-based objectives, and Casper's going to show an example later on a public data set, because the chemistry and process development of these batteries are some of the hottest IP topics that manufacturers are looking to protect, and so we obviously can't show you live customer data. But it's a really interesting study because it's focusing on optimizing LFP chemistries, and LFP chemistries are really gaining a lot of attention from the market at the moment because of their lower cost, which is driving their uptake in the lower end of the automotive market and also in the energy storage space. So if we take another look at how you might cut the cost saving and the time saving, and what really drives the R&D costs. Last year, McKinsey issued a report that called out test and validation as a key challenge in getting batteries to market. And we might go and infer from that then that a large chunk of the R&D costs are associated with testing and validation, and indeed that testing and validation effort has the opportunity to have a large impact on time to market. Certainly, when I was working in industry, OEMs recognize the challenge of testing. They recognize how much it costs, and so it's very common now to have a team dedicated to looking at optimizing that testing process, and that's very much a growing space within test fields around the world. But there is still a lot of manual judgment. There's a lot of engineering judgment, good or bad, and one of the challenges that those teams will often run into is directors coming in saying, "Well, great, you've picked out these tests, or you've done this design of an experiment. How do you know it's good? How do you know? Can you mathematically show me how that works?" And that's where we're using AI to help produce data-driven models that are able to show and help convince managers that we've covered the right design space. So that's really where we've been focusing. We've been focusing on the test and development space and helping clients across the product development lifecycle. So just to call out where we've got applications across the battery development space, we're going to focus today on the far left-hand side. How do we get to the right formulation? How do we get to the right chemistry and process parameters from millions, probably billions of design possibilities? We are also doing an awful lot of research and development with clients around state of health and state of charge modeling, and that's got particular challenges with LFP chemistries with the flat voltage curve. The moving a little bit on to the right, the tool I needed when I was a test engineer was around how much data we've got. We often see in test fields that we go from having not enough data to so much data we can't look at it. I used to walk into our morning meeting and was immediately confronted with the customer question of, have you checked the data? And now if you imagine you're monitoring 200 different cells with maybe 4 or 5 parameters each on a test stand, that's 1,000 different parameters. How is any engineer going to keep an eye on 1,000 different parameters and do a good job of analyzing it? And as we move across the right-hand side, we look a lot more at reducing the time spent testing, optimizing lifetime, ensuring that we've got the right design parameters, and starting to take that back, starting to take field data back into the data analysis to make good predictions about lifetime in real-world applications. Talked a little bit generally about what the applications in battery development are, and I want to focus in now on the specific example that we're going to touch through today. So formulation. The biggest challenge here is how many parameters there are, how many outputs. So we'll probably be trying to hit energy density, power density, different fast charging. There's probably a cost element. So we've got a lot of different things to optimize for. And we've got an awful lot of variables that we can take in at the start. So all of the different chemistry parameters. The decisions that you'll make here in this very early stage are going to have a huge impact, though, on your product at the end, because the chemistry and the process is going to have far-reaching impact. It's going to affect the future competitiveness of your cells. And the way you do this research in the early stage is also going to have impacts on, for example, the size of the lab you actually need to do this research. So the capital investment you need to make in labs. It's possibly also going to have an effect on the equipment that you might need to produce the cells. So if you get that wrong, you could have a huge capital cost impact. And it probably will also have an effect on the manufacturability of your product. So that can hit you quite late in life in development. Probably a good question to ask Northvolt. But if we come back just to looking at the chemistry parameters, we could probably easily say that there's well over 1 billion design possibilities in this space. And this is just the chemistry. We're hearing more and more from customers around the world that they're realizing the importance of the process parameters in the manufacturing and the formation step that also have a significant effect on the performance and lifetime. And that is only going to become more complex as we get into different chemistries and things like multi-layer cathodes coming through as well. Now, no one's going to go and test 1 billion design possibilities. No one's got a lab big enough for that. So what's actually going to happen is we're going to narrow that down from a very large number to something probably maybe in the hundreds or maybe even fewer. And we need to be confident when we do that we're testing in the right space. And that makes the director's question, why did you pick this number of tests? Why do we know that we're not going to miss something critical? A really hard question to answer. And so with that, having explained maybe a little bit around the complexities, I'm actually going to hand over to Casper to talk us through the example of the data set we've got and go into the technical detail on what we've done.
Thank you, James, for the wonderful intro into the challenges of battery material design optimization. On a more technical side, I will be walking you through a real research case study and how we've replicated it using the Monolith AI platform. So Let's start with a little bit of context. The work we're looking at today comes from a research paper by the University of Warwick. It's exploring the complex relationship between electrode formulation, processing, and performance in lithium-ion batteries. The researchers set out to optimize lithium ion phosphate, LFP cathodes, by adjusting multiple variables, things such as the amount of binder, the conductive additives, and processing parameters, and observed how these changes influenced properties like adhesion, resistivity, and electrochemical performance. What makes this problem really interesting and really difficult is that it's a multi-objective optimization problem. Improving one parameter often comes at the expense of another. So, for example, increasing the binder improves adhesion but worsens conductivity. Adding more conductive additive may enhance rate performance but reduce energy density. So the question here is, how do you find the best balance between competing performance metrics? And that's exactly where a data-driven, AI-powered approach can make a difference. So I'll now jump into a demo that I've created on the Monolith platform. So what you're seeing here is a notebook I've created within Monolith using real experimental data from the research paper I just mentioned. Our platform allows you to create custom notebooks using these cells that include a range of manipulators ranging from data exploration, data transformation, all the way through machine learning modeling. And in this session, I'll walk you through how we can use this platform to explore the design space and validate the experimental coverage, identify some key correlations between inputs and performance metrics, train predictive models to understand system behavior, and finally recommend optimal formulations and future tests to accelerate the development cycle. So let's dive into the workflow and see how each step turns the raw data from this research paper into actionable insight. Just a brief dataset overview. So this dataset captures the complex interplay between electrode formulation, manufacturing parameters, and performance in LFP cathodes. It contains 30 key variables spanning across the composition, the processing settings, the mechanical integrity, electrical properties, and the electrochemical performance. And by linking all of these diverse parameters, the dataset provides a robust foundation for applying data-driven optimization techniques to improve battery design and accelerate R&D. So I have uploaded the dataset into my notebook here. And to take a closer look at what's in the dataset that we're working with, we have 17 unique experimental entries, and they all represent a combination of material composition and processing settings. So on the formulation side, we have 4 key ingredients, starting with LFP, our lithium iron phosphate, that acts as a active material in the cathode. We have the KS6L, a form of conductive carbon black that supports electron transport. We also have the single-walled carbon nanotubes, and they are used as an advanced conductive additive known for their high performance. And last but not least, we have the PVDF, which is a polymer binder that helps maintain the structural integrity of the electrode. In terms of processing parameters, we've captured the blade gap, the coating speed, and then the slurry viscosity. And all of these influence the electrode's final structure and manufacturability. And for outputs, we're measuring a range of important properties, including the adhesion strength, the porosity, the electrical resistance, and metrics around the particle dispersion. Finally, we've also got the electrochemical performance, and we are looking at discharge capacities recorded at multiple C rates, from a slow discharge at 1C/20 all the way up to fast discharge at 10C. So we can also visualize this data set in a table here. So these are our entries that we have for each unique mix, and we can see all of the different output and input parameters that are included. The first thing that we should do before training any sort of models on the platform is it's important to understand the design space we're working with. So firstly, using a 3D point plot, we can visualize the different material compositions tested. And this gives us a clear view of how the experiments cover the formulation space. And here we can see that there's a good spread of points across that space. I've visualized 3 of the materials used here specifically. I'll then move on to...
Sorry, Casper, just before we move on,
Of course.
I want to draw a bit of attention to the comment you just made that this is a good coverage of the design space. And I know that you've looked at many different client projects and you know what we typically see in terms of design space coverage. Can you comment a bit more on how this compares to other design spaces you've seen? What are we typically looking at when we see our client data sets?
Yeah, of course. That's a great question. What I would say, what we usually see is more of a factorial design of experiments.
Mm-hmm.
That is, clients will usually vary one input at a time whilst keeping the others constant. And, this is a very logical and systematic method from a traditional engineering perspective. But to me, it presents 2 potential challenges for machine learning. Firstly, we usually see a small number of tests that have been run. And in that case, this one variable at a time approach tends to create a more poor coverage of the overall design space. And that's, of course, a problem because machine learning models rely on varied combinations of inputs to learn the complex relationships between the parameters. On the other hand, if it's a full factorial design, and what I mean by that is where all possible combinations of inputs are tested, clients often end up running, more tests than necessary, which is both time and resource intensive. So the key takeaway for me is always that neither undersampling nor oversampling is ideal. What we encourage is a more strategic, model-informed approach to experimental design, and one that's optimized for how machine learning learns. And that's exactly what we'll explore later in this demo when I introduce a Monolith tool for intelligent test planning and next test recommendation.
Right, perfect. Yeah, so it's all about that balance of how do you make sure you're not testing too much and wasting your resources and, doing experiments where you already know what's going to happen, and balancing that against, are you exploring your design space enough to know what's going to happen and having all the information there for your modeling. Okay, thank you for that.
Absolutely. Thank you, Simon. So I'll move on from our 3D point plot here, where we visualized a few of our input parameters being the material composition. We also have a parallel coordinates feature on our platform, and this helps us visualize all of the variables at once. This kind of helps us frame the complexity of the problem, as we're not just dealing with a few inputs, but a wide range of interconnected parameters that affect the performance. This step is key because it ensures we have diverse data which supports accurate learning and ultimately better generalization when the model is applied to new design scenarios. So within this feature, it is very interactive. So as I've kind of selected here, we can look at certain areas within the design space. So if I was looking at a certain concentration of LFP and I wanted to see what the tests looked like across the other parameters, I can select that there and it will highlight the experiments that I'm looking for. So We can, of course, explore our design space in a few different ways. And once we've explored the design space, the next natural step is to uncover some relationships between inputs and outputs. And that's where Monolith's intelligent correlation features comes in. This tool it allows us to instantly identify which parameters are most strongly linked. It works by fitting mathematical functions to the data and extracting statistical metrics to quantify the strength of those correlations. So if I scroll down here, we'll see a heat map of some of the material inputs and the processing inputs I've selected against some key output metrics. If I click on a certain cell, it will show up the data points here and the function that has fitted to that relationship specifically. If I go back to the heat map, we can see a high correlation between the PVDF content, which is the polymer binder, and the adhesion strength, which makes perfect sense, as they directly influence how the electrode sticks to the current collector. We also observe a high correlation between the WCNT, the single-walled carbon nanotube content, and then the volume resistivity. Again, this is expected since the single-walled carbon nanotubes are used to enhance electrical conductivity. And insights like these help us validate the data, but also guide our focus as we begin building the predictive models. So now, with a good understanding of the data and the key relationships in place, we can now train a predictive model. And in this case, we use the material composition as an input feature. And we train the model to predict several key performance metrics. Specifically here, I've used the adhesion strength, the electrical resistivity, the area-specific impedance, and then the discharge capacity across 1C. And to evaluate the model's performance, we usually hold out a portion of the data as an unseen test set. And this allows us to measure how well the model generalizes to new untested combinations. We can assess the accuracy using different metrics. Here I've mentioned the mean absolute error and the R-squared. So to show you what this looks like, I have separated out my dataset into two datasets, one larger trained dataset, and then a few tests I can validate my model against. I've trained a random forest regression to use my material composition as my inputs and looked at the key performance metrics I have just mentioned, and then validated it against my unseen data. The mean absolute error values here, of course, differ in scale. They always differ in scale depending on the output. Naturally, the adhesion and then the discharge capacity are measured on different orders of magnitude. So we can also use the R-squared, which gives us more of an intuitive view of the overall model quality. In this case, the model achieves an R-squared of around 0.75, meaning it explains roughly 75% of the variance in the outputs, giving us confidence that it's capturing meaningful trends in the data. And now that we have trained the model, we can begin applying it across different features in the Monolith platform to explore, to predict, and to understand system behavior in more detail. Firstly, we have the scalar prediction, and this allows us to interactively test how changes in our individual inputs affect performance metrics. So here we've got dials of the different performance metrics I have been outputting in my model. And then at the bottom, we'll have a scale of the the material compositions. So for example, I can change my single-walled carbon nanotube content, and this will update my parameters here where I can see how that will affect the key performance metrics I'm interested in. And this helps us because we can reduce the reliability on physical testing. And if there is a certain test that we're interested in, we can quickly go here, change the input parameters, and see how that will affect our performance metrics. We also have a surface prediction feature on the platform. And this allows us to interactively test how changes in the individual inputs change with a certain output. So specifically here, we can visualize complex interactions, specifically how the LFP and the SWCNT composition affects the volume resistivity. And we can clearly see there is a nonlinear relationship here. As expected, the single-walled carbon nanotube content has a significant effect on the volume resistivity because of its effect on the conductivity. But we can see that there's a sharp drop in resistivity around the 0.1% concentration mark, and that aids us in our formulation and knowing we should probably aim for a higher content than 0.1%. Finally, here I've also included a explain predictions feature, which we can quantify how much each input contributes to a specific output, offering a level of interpretability that's crucial for decision making. So if we look at the discharge capacity at 1C, for example, the platform reveals that the SWCNT content is the most influential factor, and that gives us a clear guidance on where to focus for optimization. And all of these tools help us turn the model from a black box into an intuitive, interactive design assistant, helping engineers to explore ideas and make better decisions faster. Now comes the exciting bit, and this is where we put the model to work with targeted optimization. Using Monolith, we can run a multi-objective optimization to search for the material compositions that balance several competing performance targets. In this case, we're aiming to maximize the adhesion strength, retain high capacity at high C rates. We want to minimize the area-specific impedance and then reduce the volumetric resistivity. Let me just open up the targeted optimization steps so you can have a clearer look on what this looks like. So I have picked out the model that I have just trained, and I can enter some values manually for the different outputs I am targeting for. So as I've mentioned, I've inputted a high target for my adhesion and a high target for my discharge capacity at 1C, but also trying to minimize my volume resistivity and area-specific impedance. If we're looking at a specific area within our design space, we can also restrict some inputs and set constraints for individual material compositions. So for example, if I was only looking at the concentration of LFP up to 95%, I can change the slider here to only go to that 95%, and the targeted optimization will only look for design recommendations in that area of the design space. If I go back to the step that has loaded here, after the targeted optimization has iterated through many of these different designs, it will output me a table of all of my different designs that we can then test and see the different performance metrics that we get. To visualize this in a more visual way, we can also look at the parallel coordinates plot, and the gray lines are all of the different designs that the targeted optimization has iterated through, and the red ones are the recommended designs it has picked from to balance all of those different performance metrics. Of course, going back to the original problem, these objectives often pull in different directions, which makes manual optimization extremely difficult. But with Monolith, we can explore thousands of possible combinations and quickly identify the optimal trade-offs, all without running a single additional test. So once we've built and optimized our model, the natural next question is, what should we test next? And this is where Monolith's next test recommender comes in. It intelligently suggests the next set of experiments to run, not just randomly, but in a strategic, data-driven way. The platform evaluates different recommender strategies, which we will see in this graph here, to determine which one explores the design space most efficiently, helping to close knowledge gaps and reduce uncertainty in the model. So you'll see on this graph here, we'll have the number of tests, and on the left-hand side, we'll have the mean squared error on the y-axis, and we're looking for a curve that drops in that mean squared area as quickly as possible. So we want to build a highly accurate model with the fewest tests possible. Once we have the best recommender identified from this graph here, we can apply it to our data set.
Casper, just before we move on, and I know you touched on this very quickly, but this is a graph that whenever we show it to people, I think needs a bit more explanation as to what exactly we're looking at. So we see here an evaluation of our different recommenders. Could you just go into a little bit more depth as to what the recommenders are and what exactly you're looking for to show that which one is the best recommender for your use case?
Yeah, absolutely no problem at all. I think it will help if I open up this step here and show what the next test recommender evaluation looks like. So of course we use this to evaluate the different recommenders. You can see that I start off by picking out the data that I have just been using, which I use to train my model. And I will start by selecting the input features and then the target outputs we're interested in optimizing. And these are usually the ones that used in our initial model. We then choose from the different recommenders available on the platform, usually select all of them if we're not quite sure which ones we want to optimize for this specific data set. The recommenders are powered by a range of statistical exploration strategies, such as a Bayesian optimization, for example, and others that explore in many, many different ways. And each recommender is built of its own different types of explorers. We also define our training and evaluation strategy here, which is key. So this is referring to the acquisition and the evaluation box that you'll see at the bottom. We'll always start with an initial batch, and that initial batch is used to train a surrogate model. So we've got an initial acquisition batch, which we use to train the model, and then we've got our initial evaluation batch, which is used to then validate that model. With each iteration, we add a certain number of tests. And with that certain number of tests, those tests are picked out by the different recommenders, and then also from a random strategy and from an original table order. And with each iteration, the model is evaluated against that separate evaluation validation data, allowing us to track how each recommender performs over time. So if I go back to the to my graph here, you'll see that we've started off with an initial batch of 5, and I've added one test to the batch with each iteration. And each of these number of tests, you can see the mean squared error of our model. What we want to be comparing against here is, for example, our original table order. And I've picked the zeta recommender here as it decreased in mean squared error much faster than the original table order, meaning that at the maximum number of tests here, the original table order got to around a mean squared error of 1.15, and we reached that with a zeta recommender at 7 number of tests. Of course, if we get more tests here into our data set, this becomes more apparent on how many tests we can do to get to a good model accuracy. But because I have quite a small number of tests in my data set right now, I am looking at my endpoint here and wanting to extend that to the least amount of tests possible, but get to my smallest amount of mean squared error.
Okay, so the idea here is that there are all these different recommenders with different statistical exploration methods, and this graph lets you see which one has the fastest reducing error, so you can compare it to see which one works best for your particular data set and for your particular objectives. Is that right?
Yes, Absolutely.
All right, thank you.
No problem at all. So as we just touched over, we explore this and get our best recommender, which I've picked out Zeta from here. And then we can apply Zeta to the data set we have currently, and we will get a batch of next tests to complete. We can pick the amount of tests to complete. I've picked 10 here, and this becomes a very iterative process of the next test recommender will give us recommendations for new tests. We'll go test those, feed that data back into the model, and try to get to as accurate of a model as possible. And that's what we call active learning. And I think that brings me nicely back to the slides I've got here. And I would like to touch upon that iterative process a little bit more. So taking a second to compare the two different methods, we've got maybe more of a traditional approach to cathode testing with an AI guided approach using Monolith on the right. On the left-hand side, we see that conventional approach, and this typically involves those factorial campaigns that I touched upon a bit earlier, where only one parameter is varied at a time while keeping the rest fixed. It follows more of a rigid recipe-based testing strategy, often requiring a large number of physical and electrochemical tests, one after another, across, as we know, multiple dimensions like active materials, binders, formulations, processing factors. And this method is super systematic. Therefore, it's very resource intensive and slow, and doesn't really make use of the patterns that we already see in the data. But if we compare that to the right hand side here, where we see the AI guided testing workflow, here we begin by defining the design space and collecting the available data, and then the data is pre-processed and fed into the Monolith AI stack, where we evaluate various experimental combinations. We predict the outcomes, and we use the next test recommender to strategically suggest the most informative next experiments. And as we iterate, AI continuously retrains on new data, as I've just mentioned with the active learning, refining its predictions, and ultimately guiding us towards an optimal design, with a human always in the loop to make these informed decisions. And this approach is much faster, it's more efficient, and significantly reduces testing cost and time, all while improving the design outcomes. So, in short, Monolith enables teams to move from that manual trial and error method to a more data-driven, intelligent experimentation approach. So just to quickly recap everything I've just covered in the demo and in my slides, we kind of started with a real experimental data set from this academic research exploring how electrode formulation and processing parameters influence performance in LFP cathodes. And using the Monolith platform, I explored the design space to ensure we had a diverse, well-distributed data set. I identified key correlations between the inputs and the outputs using our intelligent correlations feature. I trained a predictive model to estimate properties like adhesion, resistivity, and the discharge capacity. I applied the model through scalar and surface prediction and explained my results to understand the driver variables. I ran a targeted multi-objective optimization to identify optimal material behaviors, optimal material formulations. And finally, I've used the next test recommender to guide future experiments intelligently. And all of this helps to accelerate R&D. It helps to reduce the physical testing that we do in labs and make better design decisions faster. So thank you for following this technical part of the webinar, and I'll be happy to take some questions at the end. And for now, I will give it back to James.
very much, Casper. So, just before we wrap up, I just wanted to touch a little bit on how we work with you in the different stages of development throughout this, or different stages of deployment throughout the normal approach. What we often find is that, and we touched a little bit earlier, the nervousness of engineers to fully embrace this in the first phase, without having necessarily seen the results and been able to feel and touch them. So what we often do in a stage one is to establish, go through a workflow very similar to what Casper's just talked through on a historical data set, show that there is an advantage there to be gone after. We'll then take that through into a stage two, normally on a live program, deploying that in the first program to show the range of improvements. We'll then kind of go into an efficiency optimization, looking at reducing the testing time through an early reduction of failing tests. And it's probably not uncommon throughout this stage that these are almost in a year type sense. So that this whole process takes 2 to 3 years. But what we'll then do is work with you in a kind of a fourth stage to establish that within your testing process, establish that within your test lab, so that it's a well-defined, rigorous process that continually optimizes and is deployable by your teams. So probably one of the key takeaways there is we work very closely with you throughout this process to help guide and help deliver good value and good results through it. Finally, then, I'd just like to sort of touch on the problem solution and the outcomes. So we had a problem where we've got lots of different formulations we test, millions of different formulations. Each test takes weeks, each run takes time. We've got so many interacting variables that needs a multivariate analysis. And while we didn't touch on it too much today, if we were to go into lifetime testing, that can take months or even years to complete. The Monolith solution can solve a number of challenges within this. It can generate significantly improved test plans. 40% has been easily shown using the test recommenders. It's able to identify a huge number of anomalies. Well over 90% of test errors can be detected, and we've deployed that in real-world applications, monitoring terabytes of test data to deliver outcomes for our customers of over $500,000 savings on single battery test campaigns, and given them the opportunity to go after the much bigger prize of hundreds of millions on launching products earlier into the market. So finally, I just wanted to revisit this slide but not talk to it too much. We talked about the challenges and how they were all interlinked at the start, and I hope we've been able to show through the presentation that increasing the usage of AI in these spaces can actually deliver the results that we've talked about today. And happy to take any questions.
All right. Well, thank you both for your talks. Casper and James is very insightful, and I can see we have some questions in the Q&A. So as we go through, if you have anything else that comes to mind, please submit it through the function and we'll try to get to it. But I'd like to actually start off with one key question from myself that I often hear people ask, which is, we talk here about reducing the test plan and how long it takes to complete your experiment. So that would usually result in some type of savings in not having to run as many tests. So James, I guess this is probably better for you. In your experience, what do engineers typically do with these time savings and experimental resources savings?
So it's a good question, Simon. I don't think I've ever been in a test lab where we didn't have too much work to run. If it wasn't critical, it probably wasn't in the door. So I think what most engineers would do with that time saving is to increase the efficiency of the test lab, get more tests through, more programs, more checks, and use that time. There's probably a really interesting element that if you were designing a lab from the ground up, or deploying a new lab using this technique, you could also reduce your capital investment by not buying as many test stations if you could be more efficient. So you could deliver the same quality in the same time while saving costs on your test lab. So there's an interesting element there, though I think in the majority of cases, that's probably not where people are using the savings.
Yep, that's a good answer. There is one question here that I see that's actually drawn my attention. I will skip to that one first, and then we'll come back to the others. So this is a question that we get asked pretty much at every trade show we go to, every event, every webinar, every time we post a blog or a white paper, which is the question about having enough data. So the idea here is we talk about recommending the next designs and talking about how we can explore the design space best and making a model, but everything we've seen so far is based on some type of data. So in these situations that you don't have any data to start with, or you have very little, what is the general advice here? And I guess this would be a question to you both. So does anyone want to answer this one first?
Yeah, of course. I'm happy to answer this question. I mean, it's a great question. Of course, I think I hear it day to day, being on the technical delivery side. I think the key here is to think of the whole process as more of a progressive, data efficient process. So even with a small initial batch of tests, we can start building a surrogate model that captures the basic relationships in the system. From there, of course, you can use the Monolith's next test recommender to strategically guide new experiments and selecting the most informative combinations to improve the model as quickly as possible. So, in other words, rather than needing a huge data set up front, we start with small and we let AI help us direct what to test next, maximizing the learning from minimal data. Yeah, I know in some cases we've looked at trying to use historical and simulation data if it's available and applicable, and we can incorporate that into giving the model a head start. But even with little to no initial data, we can start to recommend optimal designs by focusing on smart, targeted exploration.
No, thank you for that. James, do you have anything else to add?
It's obviously always going to be against your baseline, right? So if your baseline is running, you've always got to start with a test somewhere. So you always have this problem. I guess the difference in our case and using this approach is that we're allowing an opportunity to learn and explore at each iterative step. And that really helps in making sure that we don't spend too much time exploring areas of the design space that don't provide value, and therefore we can narrow down on the ones that do quicker.
Perfect. Yeah, so it sounds like it's even if you're starting from nothing or very little, AI is still going to help guide you how you get more and how you develop your testing strategy. And as you get more data, as with any machine learning, the recommendations get better, the whole process gets better. Perfect. This question, I think, is probably going to be for Casper. In the demo you trained on the data set, can you share what model and what configuration you used to train on the specific data set? I think you used a random forest regression, if I'm not mistaken. So could you quickly comment on the model that you trained and tell us a bit more about why you made that choice?
Yeah, absolutely. So yeah, as you correctly just mentioned, I did use a random forest regression. So firstly, a random forest handles non-linear relationships and interactions between the variables very well, which is exactly what we expect in complex systems like electrode formulation. So that was my first reasoning. I think my second reasoning is it's very robust to overfitting, especially compared to individual decision trees. And what I mean by overfitting is, when we have a training data set, we want to train a model that is very generalizable. So when it sees unseen data, it also predicts very well. Overfitting if it very, very tightly trains on the relationships in that specific data set and doesn't generalize well to the whole design space. And then also, the random forest usually works very well with smaller data sets. And as I mentioned in my demo, this specific data set from this research paper only had 17 unique mixes of the materials. So it still offers good predictive performance and interpretability, even though we only have a small amount of data points.
Perfect. I'm just looking at the time here, and I think we're going to have to wrap up in a bit. Maybe we'll just be able to fit one more question, and thanks to everyone who's submitted a question. Sorry, we're not going to be able to get through all of them. But here's a question on when we have specific requirements to perform certain test conditions. Maybe we have historical test plans or company, like how they typically do it in the test lab. If everything is already structured, is there value still to having recommended designs and all this optimization we spoke about today? Maybe James, you want to comment on this one?
Yeah, so I think if I understand the question, Simon, I guess we're saying we've narrowed the design space by having requirements from the company on what we want to go and look at. And that's fine, right? So long as there is some variation, as long as you still need to optimize a parameter. If it's fully fixed, there's no benefit, right? But so long as there is some variation within it, some things that we can adjust and explore, then there's still very much value to doing the design of experiments and using the AI approach. All we're really doing is narrowing down the space in which we go exploring.
Perfect. All right. Well, that's all the time we have for questions today. And thank you to everyone who submitted the questions. We will try to answer the rest of them either in a follow-up email or maybe we'll see them on our blog. So I really recommend that you take a look at our website because we have some white papers and useful resources for applying machine learning to engineering. James touched on multivariate anomaly detection problems earlier. And if you're interested in learning more there, we do have a webinar and a blog on that specific topic. Otherwise, if you're interested in keeping up to date with our resources, I really recommend you subscribe to our newsletter where we share new blogs, new webinars, new white papers, all on our website that you can access and take a look at. But other than that, if you found anything really interesting today and maybe you want a deeper dive of the Monolith platform and what it can do for you, there is a QR code here that you can scan to book a demo where someone from our team will be able to reach out and contact you about setting up some time to walk through what the platform can do for you. I want to finally thank James and Casper again for today and all the things they've talked about and for the technical walkthrough. It's been very valuable to see how we can perform this multi-objective problem in the Monolith platform. And thanks for explaining basically the full process. I think we went a bit longer than usual in this webinar. It's on the longer side, but I think it was great to see the full process from start to finish of how we would look at building up this iterative process. So thanks again, James. Thanks, Casper. And thanks to everyone who's joined in today.
Thank you very much, all.
Thank you.